Hi, Mr. D here doing a quick video on limits at infinity, another way to solve these problems. I like to refer to this as the Algebra 2 method. We might have learned that a few years ago in our Algebra 2 classes. But here's basically the way it works. We're looking at horizontal asymptotes. Horizontal asymptotes can also be referred to as limits because they do limit the curve from going to a specific place. And so if we have the line y is equal to L, right? L is a horizontal asymptote. On the graph of f, here's our graph of f. When the limit as x goes to infinity, it starts to get closer and closer, or arbitrarily close to L. Or if it's going to the other direction, negative infinity, then if it's going out to negative infinity, then I can also get an L value, and that will also be considered a horizontal asymptote. All right, so something simple to go on. I like to look at a set of rules. And here's this set of rules. So this usually you find this in many areas, but it's really a relationship between the numerator and the denominator that helps decide what we're going to do with these different values. So a of x to the a times x to some nth power is divided by b times x to some nth power. Now, this is the leading coefficient and the leading term. All right. There could be a lot of other terms back here, but we've got to the highest power on both the first in the first section, which is the first term now. And so these terms are organized in a decreasing manner, and so we know this is the first term. So that's important because you could have a lower term be placed in front, but that's not necessarily the leading term. The leading term always has the highest exponential value on the x associated with it. Now, the coefficient might be a fraction or a negative or whatever. That doesn't necessarily matter too much. But you're looking for the power of the x to rule the rule how the decreasing situation is there. All right. So if n, the exponential power in the numerator, is greater than m, then you will have a horizontal asymptote at y equals 0. So let me just put that. Where will the horizontal asymptote be? Horizontal asymptote. It will be at y equals 0. If n is equal to m. So anyway, this is like an x squared over an x squared. Those are equal. So you will have a horizontal asymptote at y equal the ratio of a over b. All right? If n is greater than m, meaning this power is greater than this one, theoretically we could divide into that, so it would lead us to some long division and so forth. But there's no horizontal asymptote. That would actually give us a slant asymptote. So let's look at an example. We're asked to find the limit of 2x minus 1. Now, in another video, I did another way, but this is another way yet to find this limit. So compare the exponential values of x. So what is happening with our n and our m? Well, they both appear to be 1, right? So since n is equal to m, we go back to our rules and say, oh, well, we have a ratio here. Y equals the ratio of a over b. All right, so in this case, our a is 2 and our b is 1. Since our b is 1, it's 2 over 1. Our y value, or our horizontal asymptote, is equal to 2. And thus, the limit as x approaches infinity of f of x is 2. Horizontal line asymptote, again, at y equal 2. All right, a couple more. Sorry, there's a little jittery there. Let's see if I can scoot over here now, if it'll follow me. All right. So here we have the limit of 2x plus 5 divided by 3x squared plus 1. All right. Now we notice that n, our numerator power, is less than the denominator power. So n is less than m. So we're going to go with a rule that says that it's at y equal 0. So the limit as x goes to infinity of f of x is 0. We will have a horizontal asymptote at y equal 0. One last one. Example 3, we have 2x cubed plus 5 divided by 3x squared plus 1. Now we notice here that the n value, 3, is greater than m. And so the limit as x goes to infinity of f of x does not exist. We would see that it would actually grow without bound in this particular situation because this x cubed is always outracing cubing the denominator, which is only squaring. So the numerator will continue to grow and the denominator can't catch up, and so it grows without bound. So we do not get a horizontal asymptote. We could get a slant asymptote, and we would have to divide that out, and that's not for this video. So enjoy that. That was some algebraic maneuvers, again, with finding horizontal asymptotes and thus limits to infinity. I'm D. Dykstra. Thanks again. Hope you have a great night. Peace.